Physical science time. What color should we use? Blue. Let's do pink. What can I erase what? Who said that?
No, I was talking to Josie.
Oh, you were talking to Josie. Okay, let's get started. The objective, actually usually we write this thing down first. We're talking today about thermal energy. Thermal energy is the energy of what? Heat. Heat. Like, it's hunting season, so like thermal underwear. What's special about those kind of underwear you wear hunting? You don't need them this year because it's 95 degrees outside, but they keep you warm and you want kept warm. Which is actually because of the way they are, it's your whole body except for your hands and toes, right, and your face. They're not like normal underwear. They don't just cover the normal underwear spot. They cover your whole body, and they're called thermal energy underwear because they keep you warm. Now, I have it set up in my brain, the confusion between thermal energy and thermal underwear, so I'm probably going to be repeatedly talking about thermal underwear today. So that's great. The objective is model the effects of thermodynamics. Model, hopefully this was met in your lab, model the effects, but that's what we're going to talk about today too, effects of thermodynamics. Thermal energy, I think a cooler word is thermodynamics. It sounds more Star Trek-y. Thermodynamics. It sounds like you'd have to be a better rapper to fit thermodynamics into your rap than to fit thermal energy into your rap. But you couldn't avoid either because the whole universe has to do with thermal energy. Remember there are two things in the universe. What are they? I mean, that sounds almost like philosophical dualism, which is not something I am. But what are the two things in the universe? You could say things like space and not space. That would be two things. Time, you could say, and not time. But I mean in physical science, what are the two things that we talk about? What's the broadest breakdown of two things in the universe that we can perceive?
Things.
No, you're right. There is such a thing as space, so that's nothing, or no thing. But there's things, there's matter, right? There's matter, and there's
Not matter.
which is?
Dark matter. Air.
Okay, there's also dark matter, but we're not talking about that right now. Air is matter.
Heat matter. Heat. Thermal. Light.
Energy, just energy in general. So the universe, in one schema of the universe, the things that we can break down about the universe is that everything observable, everything, what's the word I'm looking for? No, it's not thermal underwear this time. Everything that is empirically, that's the word I was looking for, observable. Everything that we can gather evidence about is either energy or matter in the universe. Remember, we talked about this at the beginning of the year, but is there such a thing as a ghost? I don't know. There might be, right? But that's not something empirically observable. And so in physical science, we don't talk about it. And I'm using the word ghost as kind of like a byword because of the contentious topic of, is there such a thing as God? Well, it's not that science is saying there is or is not, but it's not within the realm of science because it's not empirically observable. And that's not a judgment call, it's just that we can't empirically observe it. So, of the two things in the universe, matter and energy, that are empirically observable, thermal energy is one of them. Thermal energy is one of them, and the discussion of thermal energy is called thermodynamics, or rather, the way that thermal energy behaves. The different interactions that thermal energy has with the universe is called thermodynamics. One of the root words for this is thermos, which is Greek for heat, and dynamos, which is Greek for many things kind of working together. You remember dynamite. Dynamos in Greek is something that has a lot of power, and it's usually used as a way that things interact. The way that thermal energy behaves. You have a family dynamic. You know, this word dynamic is what I'm talking about right now. You have a family dynamic. Your family behaves around each other a different way than someone else's family behaves around themselves. This class has a different dynamic than my chemistry class. This class has a much better dynamic than my chemistry class. It's just, dynamic just means the different way that things interact is how we use it in science. So thermodynamics is the different ways that thermal energy interacts with its environment. We talk about, I'm trying to get to the correct page. I'm still trying to get to the correct page. What did you say, Lucas?
He said he's waiting on you.
Yeah, you're waiting on you. That's right. Thanks, Lucas. I was actually going to look for the 3+1 laws of thermodynamics, but I don't think they're in this book, and they're not on this test. But I did want to talk about them. There are. I might have to look them up. Stand by for just a second. The main thing is that I don't want to tell you something that's a lie, obviously, and I don't even really want to be wrong on video. So, oops, I made a mark in my book. So I'm going to use Wikipedia. Not funny.
Not funny, haha.
Not funny, haha. Funny, interesting. Funny, weird. There we go. Okay, so I'm going to talk about the 3 laws of thermodynamics kind of briefly as more of a overview of thermodynamics, which we will then get into. The first law of thermodynamics is that the heat energy, what's another word for heat energy? Of a system is in balance with the work put in. So there's a relationship between heat energy and work. And when I say in balance, there's a relationship between those things where they have to add up to the same thing all the time. Remember when we talked about work, we talked about how energy can be lost in the form of heat energy. Do you remember that? That if we do work with a pulley, it can never be 100% efficient because there's always going to be some friction between the rope or the chain or whatever and the pulley itself, which is going to reduce the amount of work, meaning that the heat energy will always be in balance. Eventually, over time, how will the heat energy change? Always. In any closed system, that is, system that doesn't have input or output to another system, how will the heat energy always change over time? It'll always get warmer. The heat energy will always go up because no system is perfectly efficient. With an E at the end of it, like Shakespeare would write? Come on, Tommy, give me a break. With the work put in.
What?
I think you knew that, and I think you were just pointing it out to be mean, and that's okay. The second law is that heat is the flow of thermal energy from a warm body to a cooler one. Basically, thermal energy is always flowing from something that is warmer to something cooler. And this, it's usually pretty self-evident, like usually we're pretty familiar with this in our daily life, but there are some times where it kind of tricks us. Like, I have here a little cup of hot coffee. How does this feel on my paw? Hot. Very good. You guys are really good at this. So this feels hot because this has a higher thermal energy. We might even say it has a higher temperature, but that's a separate thing that we will talk about. But it has a higher thermal energy than my hand, and so my hand feels that. The thermoreceptors in the nerves in my hand feel that as heat. That's what we feel as heat, is when thermal energy is flowing into our body. Now, when we feel something cold, is this cold? I hope it is, because kind of. It feels cooler. When we feel something cold, it's not that cold energy is flowing into our hands. What is it? There's no such thing as cold energy. It's, heat coming from my hand, into the cooler thing. So what we feel as cold is actually heat flowing out of your body. Some things feel, it's not stupid, Lucas, it's science. Some things feel, look, so everything, we can safely assume that everything in this room is roughly the same ambient temperature of 71 degrees Fahrenheit, which is like 22-ish degrees Celsius. But Tegan points out something great. If you touch this table, touch it with your hand. Does it feel warm or cold? It feels maybe a little bit cool, right? Now touch the slate blackboard, Tegan. What is that? Does that feel warmer or cooler than your table? It feels cooler. Is it? No, probably not. If we took the temperature of that, we'd find it was the same temperature as the table. What about the metal of the table leg? Does that feel warmer or cooler than the table? It feels cooler, but it probably isn't. It's probably actually the same temperature. And that's because what we feel as cold is actually just how fast heat energy is flowing out of your body. It's how fast the material is conducting heat away. So we'll talk about that more when we talk about conduction and heat capacity. But basically, even though everything in here is at the same temperature, the flow of thermal energy is what we feel as heat. Where's my black go? Does anyone know? What did I do with black?
On your podium thing.
Oh. Now what? The third law of thermodynamics is that absolute zero, I'm going to put that in quotes for now. It is a real thing, but it's something we haven't talked about. Absolute zero is the temperature at which energy of a system is at its minimum. It's not necessarily that nothing is moving, and we'll talk about the relationship between particle motion and temperature, but it's not that nothing is moving, it's that it's moving as very little, or it has the minimum amount of energy that it possibly can. And that's called absolute zero. Have you heard of the temperature absolute zero before? Yeah. This is defined, the definition is that it's 0 Kelvin. We use the Kelvin scale a lot of times in science because, by definition, this scale cannot have a negative. The minimum amount of heat that a system can possibly have is 0 on the Kelvin scale, and therefore there can't be a negative. But it's about negative 273.15 degrees Celsius. And it's something like 360, I can't remember, you'd have to, actually, you know what,
What's the word?
I have it right here. 459.67. Negative 459.67 degrees Fahrenheit. So these temperatures, this is effectively the lowest temperature in the universe. Yes?
Isn't like the vacuum of space about that cold?
Okay, so the vacuum of space is an interesting concept here because particles, the very, very, very few particles that are in space, we wouldn't say the vacuum of space because that implies there's no particles, but the very few particles that are actually in outer space are generally moving about as slow as they can, yes. So it's somewhere within, I don't know, 5 to 10 degrees of absolute zero, I would say. And of course there can be oddballs that are moving faster or slower. It varies, but they'll only because there are so few particles in space. And then there's also, conveniently for you guys, there's also a 0th law of thermodynamics.
Oh.
So put that below the third one. It's basically the commutative property. If two systems are in thermal, I'm going to put thermal equilibrium with an E at the end, the third is in equilibrium. Oh, sorry, I shouldn't say that. The two are in equilibrium with each other. I kind of ran out of room, but basically it is if x equals y equals 2, then 2 equals x and 2 equals y. Or, maybe phrase it a better way, if x equals 2 and y equals 2, then x equals y. You see what I mean? Like if these two things are equal and they're all both equal to this third thing, then they're equal to each other also. Which seems almost mathematically simple, like it seems like something that should be very apparent, but it's really important in thermodynamics. That's why it was called the 0th law. They could have called it the 4th one, and they thought, you know what, this is more fundamental than the other 3 even, and so we have to call it the 0th. It's a law of the universe. The commutative property of algebra is the law of the universe. It is commutative property, right? Not transitive? Which one am I talking? It's transitive.
I don't know. It's transitive.
When A equals 1 and B equals 1 and therefore A equals B, that's transitive? Gosh dang it. Which one's commutative?
I don't know. Commutative is where you can two things in the parentheses. Yeah. Or maybe it's like all addition, and then you can like
let's say that this one's the 0th law of thermodynamics and leave the math, which I'm really betraying my ignorance about basic high school math in this. These are the laws of thermodynamics, and through them we talk about things like heat energy, or heat itself, thermal energy, absolute zero, and then equilibrium. We've also talked about temperature a little bit. So there's a difference between heat, thermal energy, and temperature, okay? Thermal energy is the actual, well, is there going to be room if I put it over here? Thermal energy is determined by kinetic energy and potential energy of particles. And what are the particles I mean here, probably? What particles am I talking about?
The good ones?
The good ones, yeah.
The particles of matter.
Yeah, what are the particles of matter called? God bless you.
Atoms.
Atoms, or molecules, or formula units, but they're the smallest instance of a particle of that matter. So for water, it would be a molecule. For gold, it would be an atom. But the particles that are moving, because you know particles always are moving, right? Particles always move. And that's what gives them the thermal energy. And the potential energy is basically what? The kinetic energy is basically what? We talked about this in the last unit. What they're moving. Yeah, how fast they're moving. And the potential energy, in this case, is how far apart they are from each other. We discussed gravitational potential energy as how far it is from the center of Earth for us. But in this case, since they're just particles, we talk about how far apart they are from each other. So basically, the faster they move and the farther apart they are from each other, the more thermal energy they have. Thermal energy is indicated by Q, capital Q. So capital Q equals U plus K for the particles. So it's how fast they're moving and how far apart they are. Could it also be K plus U? Yeah, and I think that's the commutative property, right? And to return to that thing, I think I remember now that Q equals U plus K or Q equals K plus U. That's the commutative property. This one's the transitive property. I got it. Comments are disabled for this video, so Mr. Snitley can't badmouth me. He would put so many bad words in the comments, I would bet. Thermal energy. What, Lucas? Why wouldn't I point like that? Thermal energy. So thermal energy is the actual amount of energy because of the particles and their motion. Heat, they're not interchangeable. We can't just use heat to also be thermal energy. We can't use thermal energy to be temperature because heat, are you all done writing the laws of thermodynamics? Yeah. Is anyone not done writing the laws of thermodynamics? Okay. Okay. Heat is a different thing. Heat is what we call, as we discussed in the second law of thermodynamics, heat is the flow of thermal energy. Heat is the flow of thermal energy. Flow of thermal energy. So what we feel as heat is thermal energy flowing into our body or away from our body, and that's what we tell as heat or cool. And just like darkness is the absence of light, and evil is the absence of good, cold is the absence of heat. It's not itself a thing, it's the absence of another thing. Temperature is a way of measuring thermal energy. And it's actually a way of measuring average thermal energy. Because if we think about thermal energy as, here's a beaker, here are the particles that are within the beaker, and thermal energy is how fast or how slow they're moving, well, it stands to reason that some of them would be moving fast, and some of them are moving fast like that, some of them are moving very slow, but the average would be a set amount. Just like if I say that the class average grade in here is an 83%, does that mean every single person has an 83? No, not necessarily. And in fact, this case, it isn't. It isn't that they're all moving 83, or they're all have a grade of 83. In the same way, saying that the the temperature of this is the average thermal energy doesn't necessarily mean they're all moving at exactly the same rate with exactly the same distance between them. It just means on average that is happening. So temperature is a way of measuring average thermal energy. Heat is the flow of thermal energy, and thermal energy itself is governed by the way the particles are in a substance. We have 2 more things to talk about, and we have only 3 more minutes to do it, so let's get cracking. The main equation that we do with this, the main math for this is another instance of our friend delta. Q equals mc delta T, where Q is, what I already said, what's Q? Thermal energy. M, well guess, what's M? Mass, measured in kilograms. C is specific heat, which is measured in joules per kilogram Kelvin. So joules over, let me write that as a better fraction that's actually legible for one thing. Joules over kilograms times Kelvin. And then what's delta T? Change in, nope, capital T, change in temperature. And what do we measure temperature in the SI? I just told you already. Celsius is okay, but for this it needs to be in Kelvin, because if we use a negative temperature, we can end up with a negative thermal energy, but it throws everything off if we end up with a negative. So if I have C, which is joules per kilogram Kelvin, multiplied by M, which is in kilograms, and delta T, which is in kelvins, what do I measure my thermal energy in? No. The kelvins drop out between C and delta T. The kilograms drop out between M and C, so what's left? Joules, which is a measure of energy, and so that makes sense. So we can calculate thermal energy. Could we manipulate this equation to find other things? Yeah. In fact, this is a really nice, simple one to manipulate because it doesn't have any division right in it, and so it's a nice, simple one to manipulate. And then very briefly, the 3 ways that heat can happen, the 3 ways that thermal energy can transfer are radiation, where it comes out from a single source, which is the only one that works in a vacuum. Conduction, which is where they're actually touching each other. The objects that have thermal energy are actually touching. And convection, where it flows as a fluid flows, as a liquid or gas moves. And those were vocab words. You should know those. We didn't have time to talk about anything you guys did in your lab, but I do appreciate it. I hope there's a basic recollection of your lab as we talked about these things. And we'll talk about them more as we go over your worksheet tomorrow. Or as we work on your worksheet tomorrow.